The verification session is starting. The first speaker is Ana Carolina Silva, and is going to speak about execution time program verification with tight bounds.
So, as I was saying, I'm going to present a work I developed with Manuel Barbosa and Mario Florido, where we developed a logic capable of verifying a program's execution time with tight bounds. I'm going to first start by telling you the main motivation that led to the development of our work. So, applying formal verification to prove correction and termination of a program has already been studied extensively. However, there is another property that has been growing in relevance as a proof target, and that is resource usage. Here, when we talk about resource, we may mean time, and, energy, or memory. And this is particularly relevant in areas such as critical systems and real-time systems. So, with this in mind, we set the main goal of our work to define an axiomatic semantics capable of proving limits on the execution time of programs. But before I present you our logic, I'm going to start by giving some background on our work. So, formal verification refers to using mathematical principles to prove properties on a program. Here in particular, we focus on OR logic. So, in OR logic, it's usually used to prove correctness and termination of a program, and it makes use of a structure called the Hoare triple that's composed by a precondition, here represented by P, a program S, and a postcondition Q. And it can be read as, if a certain P is true before program S is executed, then postcondition Q will be true when the program ends. So, with this in mind, we wondered if it would be possible to do an adaptation of this logic. So, in addition to proving correctness and termination, we could also talk about resource consumption. So, this is not a novelty. This has already been done by a few works. And here I would like to highlight one that served as an inspiration for the work we developed. And this was a work developed in the Easycrypt platform. So, Easycrypt is an interactive platform that allows the demonstration of proving basically cryptographic programs and in protocols. And it started with 4 initial logics that allowed proving probabilistic and possibilistic programs. And it was later on extended with new logic, the cost-aware Hoare logic, that allowed proofs on resource consumption. It was in this logic that we based our own definitions. So, let's now look at the logic we developed. So, the first thing was an adaptation of the classics Hoare triple, where the first adaptation we made was to restrict ourselves to a very small and simple subset of statements for our language. So, we allow assignments, arrays, sequence of instructions, if then else, and while loops, and nothing else. In the pre and post condition follow the classic Hoare logic definition, where if S is executed from a state that validates precondition P, then it will lead to a state that will validate postcondition Q. But in order to be able to talk about execution times, we have another expression, a time expression T to the right of the postcondition, that will represent, it represents a limit on the time, on execution time of program S. So, having this new structure, we're now able to define some new derivation rules for our logic. And I'm just going to focus on the time expressions here highlighted. I'm not going to go into the correctness proof because that's trivial and it's the classic definition. So, let's look at the sequence rule. The sequence rule is pretty simple. So, if we have a sequence of 2 instructions, the cost of this sequence will be given by the sum of the upper bound of executing statement 1 and the cost of executing statement 2. For the if rule, since we can't statically know which of the branches is going to be executed, we need to consider the most costly branch. Therefore, we consider the maximum between the cost of executing statement S1 and the cost of executing statement S2. And to that, we add the cost of evaluating the condition of the if B. The while rule is a bit more complex, mainly because the information we have is not enough to carry out the proofs. So we need to provide some extra information. The first thing we need is an invariant for the loop, and this will allow us to prove the correction of our program. We also need to define a variant, here we represent it as f, that's a positive value that must increment with every iteration of our program and is limited by a value n. This variant will allow us to prove that our loop indeed terminates. And n represents an upper bound on the number of iterations of our while loop. So all we did left was define a function of the time of the loop's body. We could have used our logic to derive automatically our body's upper bound for the execution time. However, we decided to define a function because it gives us a bit more precision, especially when we talk about nested loops. So this function represents the cost of the body of the loop, the statement S, for every iteration. And with this, we can define the cost of the while as being the sum of the cost for every iteration of the loop's body, plus the evaluation of the condition for the while, b, n plus 1 times. And here we arrive to a logic that allowed us to prove limits on the execution time of some classical algorithms, some of which I'll show later on. However, we started wondering if we could refine a bit more our estimation. In particular, when we talk about the while rule, if we could make it a bit more refined. And to achieve that, we started wondering about using amortization. So to give a brief recap on amortized analysis, in amortized analysis, we're concerned about the worst case for a sequence of instructions instead of the worst case for each individual instruction. And this is particularly interesting when we talk about programs where some instructions are way more expensive than others. And the amortized cost for each instruction may be more or less than the real cost for each instruction, but the sum of all amortized costs will be always greater or equal to the real cost of the sequence. There are 3 typical methods applied for amortized analysis. Here we chose to focus on the potential method. In the potential method, we consider a function that maps from the structure, the state of a structure to a value. And we define the amortized cost as being the real cost plus the variation in potential. And with the restrictions that the potential is equal to 0 and it has to remain positive for every state, then we have that the sum of all amortized costs is indeed greater than the sum of the real costs. So, having this brief recap on amortization, it's left to say how we can apply it to our logic. So, we do it in our while rule, and for that, we define a potential function that must meet the restrictions we already set. So, it has to start at 0 in the beginning of the while, and it has to remain positive through every iteration. And we also define a constant value, a, which represents the amortized cost for one iteration of the loop body. So, if we can prove that a plus the variation in potential is an upper bound on the execution of the body s, then we can define the cost of the while as being the sum of the amortized cost for every loop iteration, so n times a, plus the evaluation of the condition of the while b, n plus 1 times. And with this new rule, we were able to refine the results for programs usually used in amortized analysis. So, now that we got to a logic that we were somewhat pleased with and we thought could develop good time estimates, we started wondering about applications and some scenarios, and we wondered if we could develop a logic that not only can give us an upper bound for the cost of executing a program, but the exact costs of a program. And why, you may wonder, because sometimes giving an upper bound on the execution time is not enough, doesn't provide enough safety guarantees, particularly in real-time systems and critical systems. For instance, this logic could help us prove the absence of timing leakage by proving that the execution time doesn't depend on the values of secret data. So, with this goal in mind, we started by doing some adaptations to our language. So, the The few problems we had was with the if then else, because since we can't statically know which of the branches is going to be executed, we can't estimate the exact cost of executing. So we limited our if then else by restricting so that both branches have the exact same cost of execution, therefore fixing our problem with the if then else. For the while loop, since we can't know the exact number of iterations, only an upper bound on that number, we had to completely remove it and replace it with a for loop where the number of iterations is deterministic. And with these restrictions to our language, we were now able to do the necessary adaptations to the logic. In this case, we only did adaptations into rules, the if rule and the addition of a new for rule. The if rule is simpler than the previous rule, because since we no longer have to compute the maximum between both branches, since they have the exact same cost of execution. Therefore, we can define the cost of the if as the cost of executing one branch plus the cost of evaluating the value of b. The rule for is a bit long and intimidating, but we broke it down in two rules. The rule above is executed when the condition of the for is met, so when a is less than b, and the rule below when a is greater or equal to b. So in this rule below, if we focus on this highlighted part, it says that the cost of evaluating the for is the cost of evaluating this condition of the loop, therefore a less than b. In the rule above, we have to evaluate also the condition of the loop, but not once, but b minus a plus 1 times. So for every iteration of the loop, plus 1 extra time. The rest of the time expression for the for represents the cost of updating the variable for the for, so I, plus the cost of evaluating the loop body. And we do this for b minus a iterations. And with these new rules, we developed a logic that gave us exact execution times. So now we would like to apply our 3 versions of our logic to some examples. But we don't want to do manual proofs because they're too long and prone to errors. So we implemented a small prototype in OCaml, where we first started by creating an interpreter for our language with support for annotations. Then, with this annotated program, we mechanized our logic, doing a verification condition generator that, receiving our annotated program, creates a set of verification conditions. As we saw in the while rule, we needed some extra information to be able to carry out our proofs, such as the invariant and the variance. So this algorithm is interactive and will request the user for the needed information to complete the proof. Given the conditions generated by our algorithm, we can pass them to a theorem prover that will try to validate our conditions. If they are all validated, then we have proved the validity of our initially annotation. So let's just look a bit into the VCG algorithm. So, as I said, this is a way to mechanize our logic. It receives a Hoare triple, and it generates a set of conditions. If all these conditions are validated, then we have also proved the validity of our triple. I present here a very simple example where we swap the values of variable x and y. And we want to prove that if x equals a in the beginning and y equals b, then in the end of the program, x will equal b and y will equal a. And we also want to prove that this program is constant in time, so it doesn't depend on the values of x or y. So it will generate a set of conditions, and for this it will call 2 external functions, VC and WPC. The VC function is a function that will generate some extra conditions that sometimes are needed. In the case of our language, since it's very simple, the only statement that will generate extra conditions is the while loop, where we need to prove invariance and variance and the time of the body. And we also have a call for the WPC. So what is this function? This function is simply an extension of the classic weakest precondition algorithm, where given a program S and a postcondition Q, we generate 2 values. The first value is the weakest precondition, so the weakest precondition necessary to, so the postcondition is valid when the program S finishes. And we also generate a second value, which is an estimation of an upper bound on the execution time of program S. So, continuing our example of the swapping 2 values, if we pass it to WPC, we get this result, which is highlighted here, that says that the weakest precondition of this program is when y equals b and x equals a. So this is exactly the precondition we had in our initial annotation, therefore proving the correctness of our program. We also it also calculated the upper bound for the execution time, here represented by 6, and therefore proving that our program is indeed constant in time. Now I'm just gonna go through some classic examples that we use to show the results of our logic. So for our classic approach, the worst case costs without amortization, we applied it to the insertion sort algorithm and binary search. And as you can see with the verified cost, we have successfully proved that the insertion sort we implemented was indeed quadratic in the size of the array, and also that the binary search is logarithmic in the size of the array. For the amortized analysis, we use the binary counter algorithm. In this algorithm, we have an array with bits that represents a certain number. So for instance, if the number is 11, the array would say 1101, where the leftmost bit represents the least significant bit. And if we focus on this highlighted part of our code, what it does is it increments by 1 the value represented in the bit array B. So how does it do it? It iterates from left to right and flips every bit from 1 to 0 until it finds the first bit set to 0. And when it finds this bit, it stops the iteration and flips it to 1, incrementing the total value represented by 1. So as we can simply see, the worst case cost of this small part of our code is log of n. Let's now look at the whole code. So what the code does is it starts with an array where every bit is set to 0, and it iterates n times until the final value of the array is value n. So it counts from 0 to n, and as we can see, we have an external while that iterates n times, and in this n times, we do that section that we saw. So we do an increment of the value in the array. As we saw, the increment is log of n. If we repeat this n times, the cost should be n log n. However, if we analyze this section here, we can see that the first bit flips every iteration, the second bit every other iteration, and the third bit every fourth iteration, and the fourth bit every 8, and so on if we had more bits. So we could represent the number of times every bit flips as n over 2 to the I. And if we add up the total number of bit iterations, bit flips, we would get this. So we can see that we have like a series, and it's limited by 2 of n. So the worst case cost would be linear of this algorithm and not n log n as we initially assumed. So the result that we get, if we had used our original worst case cost logic, would be n log n. But with our amortized logic, we were able to prove a linear result for our implementation. Finally, for the exact cost, we just implemented a very simple range filter. So we have a list with values and a range, and we simply filter the values that are within the range. So this is obviously linear, but we also prove the exact cost of executing this program, not only the magnitude, but also the exact cost. Just to recap and summarize some of our contributions, so we developed a logic that was able to generate a limit on the execution time of a program, and then we extended it so it would calculate amortized costs, so we created tighter bonds to certain algorithms. And finally, by restricting our language, we were able to develop a logic capable of computing the exact cost of executing a program. All these logics were proved sound, and then we implemented we did our implementation in OCaml, so we were able to run these logics with classical examples. Talking about some future work, since we developed 3 different versions of our logic, we would like in the future to do a single system which captures all our logic together to get a more cohesive implementation. Also, our prototype was a very conceptual one. It's not very efficient, so we would like to do a better one in the future and create an actual practical tool. And for that, we also need to extend our language, which is very simple and could use some additions such as functions and other data structures, so we could create more expressive programs. And finally, the initial inspiration was Easycrypt, so we would also like to apply our programs to some more complex case studies, such as cryptographic implementations. Thank you all for the attention, and I would love to answer any of your questions.
Just a curiosity, how hard do you think will be apply your logic to cryptographic algorithms?
Sorry, I didn't understand.
How hard will be, or if it's not hard, to apply your logic to cryptographic algorithms? You have to do a lot of work, or?
We will need to extend our language a lot, so our inspiration was Easycrypt, and they already do it. They already prove time constraints over cryptographic implementation, so that would be our goal in the future, but we focused on a smaller subset, so we could focus on the formalization and the soundness proofs, so now we would need just to extend, but it is possible, it's just a bit more work.
Okay. One question?
Just a related question to that. I was curious if I guess in practice whether requiring both sides of an if to have the same time. Do you think that's something that could be possible in practice, or do you think that might be a strict, difficult limitation?
It's something that sometimes is already used in security, so it will be a bit harder than just implementing a program as it comes to our head, but we just had to put some null instructions so we could guarantee that both branches at the exact same time.
Thank you.
More questions? Okay, that's the speaker.